I've mentioned it quite a few times, but your report is now online. It's been sent to you, at least by email. If you haven't got one, talk to me about it. I'll try and figure out why not, maybe change the email I'm using. Second thing is the solutions to it are online, so you can go and have a look and see what you did or didn't do. But today, we are starting our new section. In fact, this is the last section for chapter 3. And then we just have chapter 4 to do. So we've done chapter 2 and 3, so sort of a 2/3 of the way through if you count them by chapters. And what we're looking at is logarithmic and inverse trig functions. They have no real connection, and they could quite easily have made the logs one section and then had a small section, because inverse trig functions are a little bit, there's less in it, and they could have done a second section like that. But they're all together, so that's fine. To give you an idea of how small the inverse trig functions are, those questions are right at the end, so you can see there's only like 4 of them, whereas the other 22 questions are all to deal with the derivatives of log functions and connected log functions. Well, hopefully you know the log function, but I think it's probably a good idea to just do a recap of what it looks like. The most common used log function is sometimes called the natural log. It's also called log to the base a. And that's the one that in calculus we use almost exclusively. But you can get logs to the base 10. They get used occasionally in log to base 2, maybe once or twice. So we're going to look at all logs, but focus mostly on natural logs. Now, if you remember your 141 days, which probably feels like ages away. That's what the natural log function looks like. In fact, that's what all of them look like. They all have that basic shape. And they have a single x-axis intercept at 1. And they have a vertical asymptote here. So as x gets closer to 0, the natural log of x becomes negative infinity. It's not the biggest, weirdest looking curve in the world, but that's what it is. Now, if you wanted to know, for instance, what the natural log of 5 was equal to, well, it's a number. Let's call it a. So the natural log of 5 is a number. Let's call it a. And it has the property that e to the power of a is 5. So the natural log of a number tells you what power of e would give you that number. So if you try to get your head around what the natural log of 20 is, right, it's the power of e that would get you 20. Right, so would e to the power of 4 get you 20? Would e to the power of 2.7 get you 20? Well, that's what the log would be. It would be that. Now we're going to be using what are called the law of logs in a few questions. We're going to be using them to help us differentiate. We're also going to use the law of logs to do style points of the answer to make them look pretty. So here are the 3 laws of logs. The first one says the natural log of a plus the natural log of b. So you can add 2 logs together and you get a single log that is the natural log of ab. Have you seen that guy before? Yeah, you recognize that rule? First law of logs. Second one says that the natural log of A take away the natural log of B is the natural log of first guy A divided by second guy B. Third law of logs says that n times the natural log of A can be written as the natural log of A to the power of n. And what these three laws do is they allow us to take a log and break it apart, which is going this way, or to take two or more logs and combine them into a single log. And both those processes do get used today. Now, some other features of logs. These don't count as laws of logs, but they are useful to know. What number, and it is a number, is a natural log of 1? So what power of E gets you 1? Because that's what the natural log of 1 is. What power of E gets you 1?
0.
And that is this guy. On the graph, I'm pointing at that point now. Do you see the natural log of 1 is I is 0? This will happen now and again, so it's useful to know it. What number is the natural log of E? So say to yourself, what power of E is equal to E? Bit silly question to ask, but ask it. What power of E is equal to E? Any takers on that one? It's a number.
1.
Yes. And the last one. Oops, better do it down here, Adrian. You'll sometimes be dealing with ugly logs with square roots, maybe cube roots occasionally, but mostly square roots. And when it's written that way, it is not very helpful for differentiation. So square roots are the equivalent of a half of a log. And I'm actually just using a version of number 3. Isn't an actual log of e to the half a half log a? E to the half just means square root. So that's kind of our building blocks of what the log function looks like, what it means, and some of the ways in which you can manipulate things that contain logs, called the law of logs. Now, when you are differentiating logs, you are going to be using product rule, quotient rule, chain rule, and there'll be your typical go-to guys, along with some algebra like this. So let's show you what the derivative of the natural log of x is equal to. Oh, that might have been a surprise. The derivative of the natural log of x is just 1 over x. It's not very intuitive that it would be equal to that, but it is. You will see sometimes, and in some textbooks, they put an absolute value around the x. Do you see that? We'll be a little bit lax on the absolute value of x rule, but will you bear in mind that WebAssign is sometimes finicky? So if you get an answer like, and you write this and it doesn't like it, will you rewrite the answer with the x bit with an absolute value around it, and it might choose to like it. Now, the reason that they have the absolute value is to do with the log function. The log function is not allowed to be negative. It doesn't exist, right? There's no natural log of -10, right? It doesn't exist. And so this here stops that from happening. It just makes sure that the derivative is only going to be positive. And if somebody sticks -x in here, won't it become positive anyway? So it's a bit lawyer-esque, but to keep the math people happy, they sometimes do that. Me personally, I use that, and I just have a rule that's unwritten or unsaid, and that is, you should never calculate a derivative for a value of x that doesn't exist. I'll show you what I'm getting at when I say that. If I said to you, find the derivative of the square root of x, you would first convert it into x to the half, and then you do the power rule, multiply by the power, reduce by 1, and then you make it look pretty. Agreed? Would you ever use that function for x equals -10? Well, the answer is no, you should never do that. Would you agree that the square root of x function only exists for positive x's? Now, when we do the square root of x, do we ever say to people, don't use it for x equals -10? Don't we assume that nobody's going to be dumb enough to try and use it for a place where the curve doesn't exist? So that's why I stick to this one. I'm going to assume that you're never going to use your value, your derivative, in a place where the function does not exist. So here's our first example of finding a derivative. The natural log of 7 plus t to the 6. So product, quotient, or chain rule. This is the natural log, and this guy in here is my inside function. So I'm going to be using the chain rule. So the derivative is 1 over the inside function times the derivative of the inside function. Well, if you differentiate 7 plus t to the 6, you get 6t to the 5, and then you make it look pretty. And that's our first derivative. So if you want to find the derivative of the natural log of ugly guy, it's going to be 1 over the thing, right? 1 over the inside function times the derivative of that function. Try another one. Suppose I wanted to differentiate x cubed, take away x squared. That would be a chain rule. It's 1 over x cubed, take away x squared, right? 1 over what we call the inside function times the derivative of the inside function. And this would be 3x squared, take away 2x over x cubed, take away x squared. And that is definitely the answer. In this question up here, there wasn't anything you could do. That's as good as that's going to get. Is there anything that you can do with this guy to make it look pretty? Any style point that you can do on this guy?
Factor 1x.
Okay, from the top, from the bottom, from both?
All.
Okay, so you take it out of the top, you got that, take, well, what can you take out in the bottom? I know you can take out x, but can you do better than
Squared.
x? Yeah. And then you can cancel that guy with one of these, so there's still an x left. And now you've got 3x take away 2 on the top, and then x left over, x minus 1 on the bottom. So always be on the lookout for style points. Make it look like the original's probably not going to be a big issue, because it doesn't look like the original, right? Because logs distort the function. But can't you at least factor the heck out of it? So if that is possible, you should. Let's try a different one. This is question 2. And this is 5x, the natural log of 2x, take away 5. Oops, take away 5x. And I want to differentiate it. Well, differentiate this guy is easy, it's just -5. What methods will I use to differentiate 5x natural log of 2x? Product rule, quotient rule, chain rule, what method shall I use?
Product rule?
I would as well. So you've got, this guy's going to be f, and this guy's going to be g. I'm going to do the working at the side here. So f is 5x, and f dashed is 5. And then g is the natural log of 2x. And I'm now going to deliberately make a mistake. Oh yeah, if you differentiate a log, it's 1 over the thing, which is. So what's missing? There's your clue. What's missing?
Oh, you need to multiply by the 2. Or, yeah 2.
Yeah, well, eventually, but by the inside function's derivative, which is what you're saying when you say 2. So, oh, wait a minute. So you're telling me, and it's correct, that the natural log of 2x is actually, its derivative is 1 over x. And then you might, and you should, puzzle about that. So we'll come back to that question when we finish it off, but let's look at this little problem. The derivative of this guy is 1 over x. The derivative of this guy, which is clearly different, would you agree log 2x is not the same thing as log x, right? It's got 2 in it, right? It's different. Yet its derivative ends up being, once you've tidied it up, also 1 over x, which sounds like something weird is happening here. Agreed? This doesn't sound right. So let me show you why it works. This is the log of 2 things multiplied. That means I can separate it out as the log of the first thing plus the log of the second thing. So actually, isn't the log of 2x just the log of a number plus log x? Can you see why its derivative ends up being 1 over x? So you sometimes will get weird answers with logs, and you might want to think, I made a mistake. You might think 1 over x is wrong, and you change it so it looks right in your brain. Like you just leave it as 1 over 2x. Or I don't know, you stick a 2 in the top, but you do something to it. You just got to trust the math. If the math says that it's equal to 1 over x, it's equal to 1 over x. So f dash g plus fg dashed. Differentiate 5x, you get 5. Leave the g alone. Plus leave this guy alone. And you differentiate that guy, you basically just get 1 over x. Take away 5. And here's some more weird stuff. And I'm taking this maybe more lines than I need. But if you take 5x and you multiply it by 1 over x, don't you get 5? Right? 5x times 1 over x, x is cancelled, you get 5. Take away 5. Does that look kind of weird that the numbers end up cancelling each other out and you're just left with 5 natural log of 2x? Doesn't look weird. You're quite comfortable with that. Okay, that's good. That's the answer. Now, question 3. I think it qualifies as just because you can doesn't mean you should rule. Now, I could differentiate this. And if I wanted to differentiate this, wouldn't this be a chain rule inside a chain rule, right? I've got the log of an ugly function. This ugly function is itself a chain rule. And if I tried to do that and I was careful, I would eventually get the right answer. But it's really ugly, right? It's like a Russian doll, a thing inside a thing. Not really easy to deal with. So what I'm going to do is I'm going to use these rules here, or at least some of them, to rewrite this in an easier to differentiate form. It's going to look uglier. In other words, it's going to look bigger. But the bits that it's made out of are going to be easier to differentiate. So here's my first rule. If I call this guy A and I call this guy B, isn't this just the log of A times B? And the log of A times B can be broken apart as the log of the first thing plus the log of the second thing. Are you comfortable with that line? I'm using this rule here in that direction, right? Left to right. And I'm going to rewrite the natural log of sine squared in a little bit more precise form. Isn't sine squared x actually just a shorthand way of saying sine x being squared? Right. Now, if I write it like this, I can now use law 3, which says the log of a squared is 2 times the log of a. So this now becomes the natural log of 144 plus 2 times the natural log of sine x. Now that was the original function. And if you wanted to differentiate that, you'd have to do a chain rule of something that also involves another chain rule, right? A chain rule of a chain rule. In this world here, it's bigger, probably uglier, but isn't it also a lot easier to differentiate, right? Because the pieces that you're going to differentiate are relatively nice. So here goes. Be careful here, trick question. What is the log, what's the derivative of the log of 144?
Is it 0?
Yes. Do you know the mistake you might have made? 1 over 144. You know, like, well, we've done it before. Isn't like the derivative of e cubed still 0, right? It's just a number. And it don't matter how it's written. So that guy's 0. Probably normally I wouldn't write 0, but this time I would. Now this is 2 times the natural log of sine x, right? So 2 times. If you want to differentiate the natural log of sine x, you get 1 over sine x times the derivative of the inside function, which is cosine x. So we are now looking at Okay, we're almost done. Always look for style points. The three rules are: make it look like the original, which won't really be applying with log functions. Second rule, factor the heck out of it. Third rule, if it involves trig, shouldn't we be looking for trig identities that make it prettier? Does anybody recognize cosine x over sine x?
Cotangent.
And so your final answer is that guy. Now, ugly function, quite a nice derivative, agreed? Try another one. This one is going to fall into just because you can doesn't mean you should rule. When there are logs of expressions inside the log, like in this case, 1 over x to the 5, or in that previous question that we just finished doing, the natural log of this ugly guy, you should think about using the laws of logs to rewrite this fella in an easier to deal with form. So here goes. 1 over x to the 5, I'm going to call x to the power of -5. Would have done that anyway, right? If it'd just been 1 over x to the 5, wouldn't have written that down. That's pretty standard. Now, one of these three rules, number 1, number 2, or number 3, is going to allow me to rewrite this in a different form.
2.
Look again.
3.
Isn't this like a, and this is like n, a to the power of n?
Oh, yeah.
So it's going to be n times. Now that I've rewritten it like this, so we had to do a bit of work up front, but now I've rewritten the function, isn't this going to be quite easy to differentiate? And its derivative, -5 over x. That's the end of that question.
I had a
So-
question.
Sure, what you got?
So for the like 1 over x to the 5, that wouldn't be like the a over b.
Oh, I can do it that way. You want to say it that way? Because it does work. So if we think of that as like a,
Oh, but you
over
have to
b.
make it x to the -5 anyway. Okay.
No, we can do it. It would work. You'd get the natural log of 1, take away the natural log of x to the 5. Now, isn't the natural log of 1 0? So what you end up with is negative the natural log of x to the 5. And then if I use this rule, won't it still slightly different journey, but don't you still end up with -5 log x at the end? So that wasn't that that was wrong, it's just a little bit different road, that's all. Make sense?
Yes.
Cool. Okay, our next one is going to be just a no frills quotient rule. So suppose we do 10 over the natural log of x. So top guy is going to be called f, bottom guy is going to be called g. So this is f dash g, take away f of g, all over g squared. You don't really need to do the working on the side, but I think I'm just going to do it anyway. Because sometimes numbers cause problems. the top function f is just the number 10. So won't its derivative be 0? And the bottom function is log x, and the derivative of that is 1 over x. So these are the pieces that are going to go in here. So it's 0 times the natural log of x, take away 10 times 1 over x, all over the natural log of x squared. We okay with that? Comfortable with that? So that's just nothing. That's negative 10 over x. And this guy is the natural log of x squared. We've got to do what best we can. Sometimes there's not an awful lot you can do, but would you agree it's probably not a good idea to have a fraction with a fraction in it, right? Okay, does anyone know how to rewrite this so it's equivalent to that, but it doesn't have this negative 10 over x on the top? It's not too hard to do. Can you see what happens?
Drop the x.
The simplest, quickest way is to realize that you're allowed to drop the x, i.e. bring it downstairs, right? If you don't like that, do you know you could multiply by x over x, a special version of 1, to get the same effect? Whatever way your brain works, that's as good as that's going to be. It's finished. Do you think we are going to leave this log function the way it is and start differentiating right away? Or do you think we're going to use some of these guys to make it easier to differentiate? So is this one of those just because you can doesn't mean you should questions? What do you think? Do you think we should be able to move it around a little bit, make it look different? Any thoughts on this? What do you think? Well, I'm going to call this guy A. I'm going to call this whole thing B. So this is two things multiplied. And two things multiplied can be separated as the log of the first thing plus the log of the second. Does that seem reasonable? Now, I kind of like that. That's easy to differentiate, so I'm not going to do any more of that. And I'm looking at this guy, and I'm seeing a power. You see, e to the power of negative 3x. And if I see a power, I know I can use rule 3. And so this becomes negative 3x, the power, times the natural log of a. And then I look at my little list. Don't know what that's done there. And do you notice that the natural log of e is a number, and that number was 1? So here is the original function. Do you see what it now looks like once you've done a little bit of algebra on it? And that's much easier to differentiate. In fact, you're finished. I guess you could combine them into a single fraction, but I think it looks pretty good as is. Any questions? Right, you can tell I'm taking these slowly, but it is a function that you're probably not that familiar with, especially using these rules to change the way something looks. So here is a version of 7 now. Natural log of t squared cosine t. This is a product rule. It's not a very nice product rule because that's f and this is g. So when I want to differentiate it, I won't be able to do any algebra to make this pretty. I just have to accept the fact that it's an ugly product rule. But when I get an awkward or ugly product rule, I like to do the working at the side. So f is a natural log of t squared. We'll figure out its derivative. And g is just a cosine. Well, its derivative is easy. It's negative sine t. This fella here is the natural log of t squared, which means that it's a chain rule. It's 2 times the natural log of t to the power of 1 times the derivative of the natural log of t. So it's 2 log t over t. And now we put the pieces. The derivative, 2 natural log of t over t times cosine of t plus the natural log of t squared times negative sine t. And it's not that much, but there is something that we can do with style points. Can you see any common factor here? This is the first expression, plus here is the second expression. Can you see even a little common factor?
Natural log of t.
And so you pull that out. It's not going to make it that much better, but it is a little bit better. So here are the terms that are left. It's going to be a negative here. It's going to be a sine t and a log t. And that's you finished. Just going to start 8, but not finish it. It's another one of those, just because you can doesn't mean you should. So you shouldn't be doing this as a chain rule inside the chain rule. Inside the chain rule, there'd be 3 of them, I think. Can anybody see, using one of these 3 rules, a different way to write that? So the log of a square root of somebody. How could you write that?
Well, couldn't you change the square root to the 1/2 power and then separate the logs?
Like the way I've just written? Yes. Now, that's still a chain rule, but would you agree it's a lot easier than it would have been if he's left it alone? So when you see logs of anything, right, I want to differentiate the log of ugly thing. Well, you look to see if there's combinations of these that you might be able to do to break it apart to make the differentiation easier. And the whole goal, of course, is to make your life easier. Well, we've just looked at how to differentiate natural logs, and by far the most common thing is natural logs. That's the kind of functions that get used a lot in calculus and many formula. But You can differentiate log to the base 10, log to the base 2 of x, log to the base 4 million, whatever base you like, x. And its derivative is one over x, which looks good. And then they tag on the natural log of a. So it's not 1 over x, but 1 over the natural log a of x. I just stuck the natural log of a at the end, because if you stick it at the front, it looks like ax and not the natural log of ax. And it's just been being funny, I guess. So for instance, if you want to find, if you want to find the log to base 3 of x plus 1, can't get e out of my brain here. Its derivative is 1 over x plus 1 natural log of 3. If you want to find the log to the base 10 of x cubed plus 2x, you'll get 1 over x cubed plus 2x times the natural log of the base, which is 10. So far, so good. Do you recognize this as a chain rule question? It's not just the natural log of 10 of x, it's the natural log base 10 of an expression, right? So inside function also kicks in, and that gets you, 3x squared plus 2. And so 3x squared plus 2, x cubed plus 2x, natural log of 10. So the major difference between a natural log, which is base e, and any other base like log 10 or log to base 2, is that you have to add this one extra term here. The answer will look exactly the same as it would be if it was base e, which is what the natural log base is, with that extra little bit. In fact, if you say the log to the base e of x, isn't the answer 1 over x, the natural log of e? But the natural log of e is 1, and that's where the 1 over x came from. So if you wondered why e is so special, why is the natural log, why is that e, which is roughly 2.712, so important? It's because it makes the derivatives so much nicer. Isn't the derivative of e to the power of x just e to the power of x, right? So if you want to have a base, e is the base if you want to keep your formulas simple. So how about this one, question 9? Y is equal to the log to the base 5 of secant x. It's definitely going to be a chain rule. That guy there is my inside function. So it's going to be 1 over secant x times the natural log of 5, right? Finishing with the derivative of the inside function, right? Oh, here's a tester. Who's got a good memory? Derivative of secant x. Derivative of secant x.
Secant.
Okay, agreed. And, oh, cancel. Don't always get that. And so I now have the tan of x over the natural log of 5. Quite nice. It's 2-liner, a little bit messy, but it's still a 2-liner. Question 10. Oh, okay. Five to the z the log to the base 5 of Z? Oh, I like that question. Make this F, make this G. This is going to be a product rule. But it's a slightly ugly one. So I'll do them at the side. Okay, we've already found out how to differentiate the natural log to any base. So this guy's derivative is 1 over Z times the natural log of 5. Okay, that's that one done. If you differentiate 5 to the power of Z, you get 5 to the power of Z times something. Can anybody remember? Because e to the Z just gets you e to the Z, right? But 5 to the Z gets you 5 to the Z times something. Can anybody remember what it would be? What goes here? Last chance then. It's also log 5. So you see when it's a power, you multiply, and when it's a log, you divide. See the reverseness of them. Right, you put the pieces together then. You get natural log of 5, 5 to Z, times the untouched G, plus untouched first guy. And when you differentiate this fella, you get 1 over Z natural log of 5. And there's not an awful lot that I can do, but I can pull out 5 to the Z as a common factor. And I get natural log of 5 times natural log of Z to base 5 plus a 1 over Z natural log of 5. And I'm not going to try and make that pretty. I'm not sure it can be. Whew. We've done it, right? We are beginning to get, hopefully, a feel for how you differentiate log functions. And hopefully, you're getting comfortable with situations when you need to do this to make the derivative easier to calculate. Now, I'm going to be having a meeting during my office hour today, so I won't be available. I apologize for that. But I will be available tomorrow. So if you want to talk about your midterm, what you got wrong, the solutions to the midterm are online. So you can look at that. And everybody should have been given a report. I sent